Welcome to iTTV for Form 5 Chemistry. Today we're going to enter Chapter 2 of our Form 5 Chemistry, and the title of our first lesson is Carbon Compounds. In this chapter, we're going to look at the variety of carbon compounds that we have. Carbon compounds are all over the place. We ourselves are considered to be carbon-based organisms, plants as well as the other animals that we have here on Earth. Carbon compounds are compounds that contain carbon inside them, and there can be two main types. One can be organic carbon compounds. These are carbon compounds that come from or came from living things, plants or animals over the years. The other type of carbon compound is what we call inorganic. These carbon compounds we find in the air, the soil or the rocks. Carbon compounds, compounds that contain the element carbon. Carbon compounds can be divided into two groups: organic compounds, starch, cellulose, protein, hydrocarbons, or inorganic compounds. Example, carbon dioxide, carbon monoxide, calcium carbonate. What is important to remember, which is a common examination question, is what are organic compounds? Remember, organic means they come from living things. And inorganic, the source is non-living things. Please make sure you remember this. Hydrocarbon, organic compounds that contain only the elements hydrogen and carbon chemically combined by covalent bonds. Sources of hydrocarbon: petroleum, natural gas. So the simplest of all the organic carbon compounds are a compound known as hydrocarbons. Hydrocarbons, which come from petroleum and natural gas, only contain carbon and hydrogen inside them. Let me just draw a molecule of a potential hydrocarbon up here on the board. So let's say that we have a hydrocarbon. Remember, it contains only carbon and hydrogen. So a simple hydrocarbon would look something like this. It will contain one or two, maybe three, maybe four, maybe 1,000 carbon. We'll just do a simple one. So let's say it contains one carbon, which is covalently bonded to another carbon like so. Then, all around the carbon, it will have hydrogen atoms covalently bonded to the individual carbons. So I'll have a hydrogen bonded to this carbon, again and again. Now, the reason that I've put 3 hydrogens here, not less, not more, is because if you remember back to your periodicity, when we learned the periodic table, carbon is in group 14. It has a valence of 4, which means carbon, to become nice and stable, will try to produce 4 covalent bonds for itself. So as you can see, this carbon here has got 1, 2, 3, 4 covalent bonds, gets its octet and becomes stable. The same will occur for the other carbon. So the other carbon here will also form 3 carbon-hydrogen bonds and get its octet. And as you can see, it only contains carbon and hydrogen atoms. This is what we mean by hydrocarbon. And we get these hydrocarbons from, like we said, petroleum or natural gas. Let's go back to the slide. Petroleum, formed by the decay of marine plants, plankton, and tiny sea animals which died millions of years ago. Petroleum is a mixture of hydrocarbons. The components, fractions, have different boiling points. Therefore, these components have different boiling points and are separated by fractional distillation. And this is something, if you recall, you learned in your science when you were in the Form 3, where petroleum is separated by fractional distillation, where the molecules with the shortest chains, so maybe 2 carbons or 3 carbons or 4 carbons, they have the lowest boiling point and come out first, followed by the ones that have longer carbon chains. If you remember, we get natural gas at the top, followed by petroleum, naphtha, kerosene, diesel, and so on. Remember, each of these are hydrocarbons, and they are separated by the process of fractional distillation, which we can do because they have different boiling points. The different boiling points are because they have a different number of carbons in them. And we'll discuss this a bit later on, and you'll understand the idea of how the number of carbons affects the boiling point or melting point of a hydrocarbon molecule. Electron arrangement of carbon. Electron arrangement of the carbon atom is 2,4. Number of pairs of electrons shared is 4. So remember, like I said over here, carbon wants to produce or have 4 covalent bonds so that it gets this stable octet. Stability of organic carbon compounds. Carbon is able to form stable covalent bonds with other carbon atoms and make long chains, or other atoms like hydrogen, oxygen, nitrogen, and chlorine. So what are we trying to say here? Well, what we're trying to get you to understand is carbon is quite unique. Carbon is able to form long chains of carbon atoms because when it forms bonds with other carbons, the carbon-carbon bond is actually very, very stable. Now, most other elements cannot do these. Most other elements can only maybe make 1, 2, or 3, or 6, or 7, maybe 8 bonds with other atoms of the same type. But carbon can make millions and thousands of millions of bonds with other carbon atoms and form very, very stable compounds. The only other element that we know that can do this is silicon, which is also in the same group as carbon. So, let's go to the board and sort of visualize what we're trying to say here. What we did here was form a carbon compound that only had 2 carbons in it. But what I'm saying to you is carbon is unique in that if I start with 1 carbon, this 1 carbon can bond to another carbon. It can also bond with other carbons like so. Now, this carbon up here can bond with another carbon. This carbon can bond with another carbon and then another carbon. And this carbon can bond with another carbon and another carbon. And then they keep bonding with other carbons. And all these bonds are very, very stable, which means we get what we call macromolecules, large molecules that contain basically a carbon skeleton inside them. Because they are very stable, they can last a long time, and we use these, or they seem to be used as the building blocks of living organisms. Things like protein, starch, glucose, being used to make very, very long chains like cellulose or incellulose, to make fibers like wool and silk. All of these contain very, very large numbers of carbons that have bonded together. They can also bond with other atoms stably. So they can bond with maybe a hydrogen over here, or bond with a nitrogen over here. Or maybe there might be an oxygen up here, or possibly a chlorine over here. So they can bond with other atoms stably as well. But the most essential point is that they can bond with themselves, carbon-carbon covalent bonds, which can stretch and produce these long chains. Hydrocarbons. Hydrocarbons are divided into 2 main groups. Saturated hydrocarbon, which has single bonds only, or unsaturated hydrocarbon contain at least one double or triple bond. Examples of a saturated hydrocarbon would be methane, and an example of an unsaturated hydrocarbon would be ethene. So now when we look at our hydrocarbons in a bit more detail, we realize that the hydrocarbons themselves are divided into two main groups: saturated hydrocarbons and unsaturated hydrocarbons. What we'll do is we'll go up to the board and sketch out or draw out a saturated hydrocarbon and an unsaturated hydrocarbon. But before we do that, we'll just clean the board. So first, saturated. And as we said, in a saturated hydrocarbon, we only have single bonds. Let's draw 3 carbon atoms connected to each other like so, with hydrogens surrounding it. Normally when we draw a structure like these, we try to keep the angles at 90 degrees for all of them, so it's nice and simple and very neat and tidy. So anyway, you'll notice that in this saturated compound, all my bonds are single bonds. So I only have single bonds. Okay, beg your pardon, really I should be pointing to this carbon-carbon bond that we're talking about here. So all the carbon-carbon bonds in here are single bonds, nothing else. Now let's have a look at an unsaturated. And once again we'll use 3 carbons. So here I have a carbon, like so. But what I've said is we have at least one double or triple bond. So let's say that this carbon-carbon bond here, I double up on it. So I've got a double bond in here. This means I have an unsaturated hydrocarbon. So I'll add my hydrogens to it. Here, and like I said, here we have the double bond that's making it unsaturated. You might also notice that there's a slight difference in how the hydrogens are represented. Once again, this is based on the fact that carbon needs to only have 4 covalent bonds. So when you draw these later on in your classes or examinations, always be a bit cautious and double check to make sure that the carbons only have 4 bonds. This carbon has 1, 2, 3, 4 bonds. This carbon here has 1, 2, 3, 4 bonds, and the last carbon also 4 bonds. So this is what we call a saturated hydrocarbon, only single bonds, and this is a unsaturated hydrocarbon which has at least one double bond or a triple bond. Alkane is a saturated hydrocarbon with single covalent bonds only between the carbon atoms. Alkanes can be represented by the general formula CnH2n plus 2. So our saturated hydrocarbons form a family of carbon compounds known as the alkanes. The alkane family has a general formula CnH2n plus 2. They have a functional group which is the carbon-carbon single bond only. Let's go up to the board and write this down and write down the general formula. So our saturated hydrocarbons are known as alkanes. So these are our saturated hydrocarbons. These are known as alkanes. Alkanes, as we said, have the general formula CnH2n plus 2, where the N is the number of carbon atoms in the molecule. The functional group of our alkane is the carbon-carbon single bond. So, let's make a note here. The functional group is the carbon-carbon single bond. And remember, they are known as saturated hydrocarbons. In the table you see, we have the value of N being 1. The molecular formula we get is CH4. The name of the alkane is methane. And at the end, you can see its structural formula. When the value of N increases to 2, the structural formula becomes C2H6. Here, the name of the alkane is ethane. And you can see its structural formula. Next, you can see when the N value becomes 3, we get the formula C3H8. Here, the name of the alkane is propane. So here we see how we work out the structural formulas for our alkanes, and then how we name our alkanes. Now this is a bit tricky, so let's go up to the board and slowly work through this. But before we do that, let's just clear the board once again. So as we said, the general formula is CnH2n plus 2. Now, when we name our organic compounds, we have a system for naming based on the number of carbon atoms that are present. So over here, this is N, which represents, like we said, the number of carbon. Just draw a little line here. When your number of carbon is 1, we use the word meth. When the number of carbon is 2, we use the word eth. When the number of carbon is 3, we use the word prop. When the number of carbons are 4, we use the word bute. When the number of carbons is 5, we use the word pent. When we have 6 carbons, we use the word hex. When we have 7, we use the word hept. For now, we'll just worry about the first 7. 8 would be oct, 9 non, and 10 dec. But for now, we'll just worry about these. So, when you apply this to the formula, the number of carbons is 1. You then have to use the formula C1, so C times 1, which gives you C. H, 2 times 1 is 2, plus 2 gives you the formula CH4. Now, when we name it, so let's put another line in here, and now put down the name on this side. When we name it, we'll always start with the fact that we're doing alkanes. All alkanes will finish with the word ane. So an alkane name will end with ane. Now, what we do is we take meth and then we combine it with ane. So we get the formula CH4, and then this will lead us to the name, and the name will be for 1 carbon meth. And because it's an alkane, we get methane. Now let's try eth. Eth is 2 carbons. So if we use the formula, we get C2. H, 2 times 2 is 4, plus 2, we get H6. The name, we take eth, which means 2 carbons, and we add ane at the back. So we get ethane. Do you sort of get the idea? Let's quickly move along. Prop is 3 carbons. So our formula will be C3H, 2 times 3, 6 plus 2, 8. And when we name it, we take the name for 3 carbons, which is prop, and then we add ane, propane, like so. Now, you might notice that as you move from one to the next, the increase that we're getting is we have 1 extra carbon and 2 extra hydrogens. So it's increasing by CH2. And this is a common trend with our organic carbon families or homologous series families, that from one to the next, the number of carbon change or the mass change will always be CH2, where the mass would be increasing by 14. But we'll talk about that a bit more later. Here also, you notice the increase is CH2. Now, just applying this, the next one would be add another carbon. This would become C4, H10. Now, if I do that again here, I get C5, H12, C6, H14, and for hept, C7, H16, like so. And what would their names be? For bute, I would get butane. For pent, which is 5, I would get pentane. And for 6, I will get hexane. And if I had 7, I would get heptane. Like so. So this is how we write out the formulas for our excuse me, our formulas for our alkanes and how we name our alkanes. Now, in terms of drawing them, well, it's straightforward as well. Remember, here we have 1 carbon. So you draw 1 carbon and then add the hydrogens around it. So you have 1 hydrogen, 2, 3, and 4, like so. And when you're drawing ethane, think eth. Eth means 2 carbons. So draw your 2 carbons first off. So you put in your 1 carbon, 2 carbons, and then add your hydrogens around it. So from now, I'm just going to simplify it. We'll put in all the hydrogens and then write in our H's, like so. So if you go up to prop is 3. Good. So just draw in 1, 2, 3 carbons. Remember, put in all your hydrogens, always remembering carbon must have 4 bonds, and then add all your hydrogens to the covalent bonds. Sorry for being a bit untidy, but we're just trying to do this a bit quickly because there's so many to draw. I hope you get the idea. Try at home to do the diagrams for butane, pentane, hexane, and heptane. Remember, these carbons that we are drawing normally are drawn as straight chains. They don't have to be a straight chain. What is essential is that the number of consecutive carbons is corresponding to the number of carbons you have. So let's take an example of hex. Hex is supposed to be 6 carbons. I could draw it like this: 3, 4, 5, 6. But I could also draw it carbon, 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 like so. 1, 2, 3, 4, 5, 6. As long as the longest chain of consecutive carbons is 6, I will have hexane. But it's common for us just to draw it as a straight line because it's the simplest way to represent our alkanes. Physical properties of alkanes. Not soluble in water. Does not conduct electricity in any physical state. Have densities less than water. So the main characteristics of our alkanes are, number 1, they're not soluble in water. Secondly, we are saying that they do not conduct electricity. Please, if you remember back, these are covalent compounds, and covalent compounds cannot conduct electricity because they do not contain any free-moving ions, correct? So, they do not conduct electricity. And in general, they have a density less than water. Now, this table shows you the properties of the alkanes and how the density increases as we go down the group. You might also notice that the boiling point increases as we go down. So, what we're trying to say here is, as the number of carbon atoms increases, the density increases, and the boiling point also gradually increases. Now, if you compare methane and ethane, the boiling point of methane is negative 162 degrees Celsius. But the boiling point of ethane is only negative 89 degrees Celsius. So why is there this general trend that the boiling point increases as we go down the group? Well, the reason is to do with how the number of carbon atoms in the molecule affects the boiling point or the melting point. The melting points and boiling points increase as the number of carbon atoms increase. As mass increases, the force of attraction becomes stronger. As force of attraction becomes stronger, more energy is needed to overcome these forces of attraction. So, therefore, as we go down the family of alkanes, our melting points and boiling points and our density increases. And if you're asked this question in the exam, why there is an increase as we go down the group, your answer should follow what we just read on the slide. As the number of carbons increase, the force of attraction increases, and more energy is needed to overcome these forces. Let's put these three key things down on the board so that we can remember them. So, let's use this space over here. Now, remember, we're looking at physical property increase. So, let's try to keep it as simple as possible. Number of carbon increase, F of A. This is just our short form for force of attraction increase. Therefore, more energy is needed to overcome these stronger forces of attraction. So try to remember it. Number of carbon increase, force of attraction increase, more energy needed to overcome force of attraction, which is why the boiling point or melting point increases. But if you're answering in terms of density, then you might just want to go number of carbons increase, force of attraction increase, there's more mass and the density is higher. Chemical properties of alkanes. Alkanes have saturated carbon-carbon bonds and carbon-hydrogen only, and they are not reactive. Key thing here, saturated hydrocarbons are unreactive. Why? Because they have single bonds only and have stable octet. So remember this, it's very important. Stable octet, because of the single bond, equals unreactive. Combustion. Alkane plus oxygen will produce carbon dioxide plus water. To balance the equation, balance the carbon atoms, balance the hydrogen atoms, and then balance the oxygen atoms. So our alkanes are actually very good fuels. Propane, butane we use in our lighters and for cooking gas at home. Octane is used for petroleum or the fuel that we put into cars. When they combust, they produce carbon dioxide and water. So the hydrocarbon, which contains hydrogen and carbon, the hydrogen contributes to your water production and the carbon for the carbon dioxide production. Now let's have a look at one or two equations for combustion and how we balance these equations. But before we do that, let's just clean the board. So let's have a look at the combustion of methane. So we start with methane. Remember, meth is for 1. So if you use the formula, we get CH4. So CH4 plus O2, because we're combusting with oxygen, will produce, now as we said, when we combust our hydrocarbons, we always produce carbon dioxide and water. So we get our carbon dioxide plus our water. Now, remember, when you're balancing equations, always go from compounds to compounds first and then deal with the molecules later. So let's start with this. We've got 1 carbon here, which means we should only have 1 carbon on this side. So the number of carbon dioxide is fine. Over here, my hydrogen, here I have 4 hydrogens. So when I go from this compound to this compound, which contains hydrogen, here I need to balance the hydrogen. So to balance the 2 hydrogens, to make it 4, I put a 2 in the front. So my hydrogens now are balanced. My hydrogens and carbons are balanced. This leaves me oxygen. I count the number of oxygen on this side. I have 2 oxygen here and 2 times 1, 2 oxygen here. So altogether on this side I have 4 oxygen. O equals 4. I need to make sure that I have 4 on this side as well. How do I do that? Well, I just put a 2 in front of my O2 and my equation is then balanced. So once again, when you're doing a combustion of an alkane, remember that the alkane is going to produce the carbon dioxide and water. Deal with those first, balance the carbon, balance the hydrogens, and then worry about the oxygens. Let's try for ethane. Ethane has got 2 carbons in it, so we get C2, remember, H double plus 2. So we get H6 plus O2 produces carbon dioxide plus water. Now when we balance this, let's start. We have 2 carbons. So let's go to the compound that contains the carbon. Over here, we should have 2. So we put a 2 in the front. Let's go from this compound with the hydrogen, 6, to the hydrogen compound over here. This has to have 6. So I put a 3 in the front, like so. Now what I get is, I have 2 times 2 here, which is 4 oxygen, and 3 oxygen here. So altogether, I have 7 oxygen. Now, in order to balance it on this side, I need to have 7. So I can put 7 over 2. Only in organic chemistry are we allowed to do these types of fractions. You can change it all into whole numbers by just multiplying the whole equation by 2, and that will change the fraction into a whole number. Let's do one more. Let's take a trickier one. Let's say we take butane. But is 4 carbons, so we should have C4 H double plus 2. So that becomes 8 plus 2, 10. Good. Plus your oxygen becomes, remember, carbon dioxide plus your water. So in order to balance this, we'll start with the carbon first. How many carbons? 4. Good. So we put a 4 here. Over here now we deal with the hydrogen. 10 balanced with 2. We put a 5. Very good. Now we count the oxygen on this side. 4 times 2 gives me 8. 5 times 1 gives me 5, which means I have 13. So to balance it on this side, I do 13 over 2. So that's how we write the equation and balance the equations for combustions of alkanes. Do the carbon, do the hydrogen, and then do the oxygens. If there is insufficient oxygen, carbon monoxide or carbon will be formed. So, CH4 plus O2 will produce C plus 2H2O. CH4 plus O2 will also produce carbon C plus 2H2O. If you get carbon being produced, you get a sooty flame. So a sooty flame is produced when carbon is produced. Substitution reaction. Hydrogen atoms are replaced by chlorine atoms. Substitution reaction occurs when a mixture of alkane and chlorine is exposed to sunlight or ultraviolet light. So the substitution reaction is really, apart from combustion, the only reaction alkanes do. The reaction is between the alkane and halogens. It can be also bromine and iodine. Let's have a look at the substitution reaction in its entirety and work out how to write out their equations. Before we do that, we'll just clean the board. So, let's say that we draw a diagram. This is the Earth. Let's say that the gas methane has been released, CH4. As this gas travels up in the air, up here, at some point, ultraviolet radiation from the sun, UV light, will come into contact with our CH4. Any chlorine gas that is in the air will then react with the methane gas in the presence of the ultraviolet radiation to do what we call the substitution reaction. So now let's draw this reaction in a bit more detail. So we have methane. Methane is one carbon which is bonded to 4 hydrogens. Like so. What will happen is this methane with the ultraviolet light will start to react with chlorine gas. So let's draw our chlorine up here. Let's say we have chlorine up here. And let's say we have a bit more chlorine over here. And maybe another chlorine over here. And let's put another chlorine in over here. Now, what happens is this. When the chlorine is exposed to the ultraviolet light, the chlorine will change from a chlorine molecule into chlorine atoms. Okay, so they will be atoms, all of these. What will happen is the chlorine over here will substitute the hydrogen over here. So what occurs is this hydrogen will come out and this chlorine will substitute it. So let's write this equation out. We have CH4 plus Cl2. Now, as I said, this chlorine is going to go over here and this hydrogen is going to come out. So let's replace this with Cl and replace this with hydrogen. So my product now is CH3 with 1 Cl, like so, plus I get HCl over here, like so. This is called monochloromethane. Methane, because it's got one carbon in it and they're all single bonds, so it must be from the alkane family. Monochloro, because it's got just the one chlorine. Now what happens is this monochloromethane will go to the second part of the reaction. So this is part 1. Let's go to part 2 now. In part 2 of the reaction, we start with monochloromethane, and this will react with chlorine gas. So let's say down here, what occurs here is this. The chlorine here substitutes the hydrogen over here. The hydrogen comes out. So let's do that substitution. Chlorine goes in, hydrogen comes out. Our product now is CH2Cl2. So I get CH2Cl2 plus HCl. I get my HCl. Now, what's the name of this? Well, this got 2 chlorines, so we'll call this dichloromethane. Get the idea? Then we go to the third part. And in the third part of the reaction, the dichloro is involved. So CH2Cl2 plus Cl2. Let's go to this area over here. Once again, we are substituting. This chlorine goes in, this hydrogen comes out. So this becomes hydrogen and this becomes chlorine. What do we get? What's our product? Now we have CHCl3. So I get CHCl3 plus HCl. What would I call this? I have 3 chlorines now. So we'll call it trichloromethane, which is also known as chloroform. Then we go to the fourth reaction where we're using the trichloromethane plus Cl2. That's up here. We get the final substitution. This chlorine comes in, hydrogen out. This becomes chlorine. This becomes hydrogen. And we've got our completed substitution reaction. My final product is going to be CCl4 plus HCl. And this is tetrachloromethane. So we go from monochloromethane to dichloromethane to trichloromethane, and finally, when the full substitution is done, we have tetrachloromethane. And this is what we mean by a substitution reaction. It occurs, and once it starts with ultraviolet radiation being the catalyst or the condition we need, it won't stop till all the hydrogens have been substituted by the halogen. That is the substitution reaction that alkanes do under the conditions of ultraviolet light. We can sort of do it in the lab, where if we take the alkane and we heat it up gently with maybe bromine water, we could also do a substitution reaction. Now, let's try some questions. What is the name and formula of an alkane with 3 carbon atoms? So remember, you got 3 carbon atoms. 3, what is the key word? Or the key word that we use for 3 carbons? If you got it, don't forget to add the ane at the back of it. And then apply the formula. Remember, the general formula is CnH2n plus 2. What did you get? Let's check the answer. The answer is propane. And the formula should be C3H8. Good? Let's move on. Why does the melting point of alkanes increase when the number of carbons in the molecule increase? Now here we did this and we worked out why there is a change in melting and boiling point. Remember, it's to do with the carbons, force of attraction, and energy. Write these 3 words down and then try to create your own answer for it. You got to write it out. Remember, the only way to learn is to actually do it by yourself. Have you done it? Okay, let's check the answer. The answer is the melting points and boiling points increase as the number of carbon atoms increase. As mass increases, the force of attraction becomes stronger. As force of attraction becomes stronger, more energy is needed to overcome these forces of attraction. So remember, carbon increase, force of attraction increase, more energy. Write out the equation for the combustion of pentane. So you're doing pentane. So the first thing you got to do is you got to have the right formula. Remember, pent means 5 carbons. So write out the formula plus oxygen. Remember, when you combust alkanes, it will produce carbon dioxide and water. Now balance your carbons. Next, balance the hydrogens. Add the number of oxygens on the right hand side and then balance it with the O2 that you've got on the left hand side. Are you done? Let's see if we've got the same answer. The answer is C5H12 pentane plus 8O2 produces 5 carbon dioxide and 6 water molecules. Final question. Write out the equation for the substitution reaction between methane and chlorine gas. So what we want is the final substitution reaction for methane and chlorine gas, which we have up here on the board. Now try to visualize the total equation, everyone. So how many methane do we have? We have just one methane. So we should have CH4 plus chlorine, Cl2. But if you remember here and you look at it, how many chlorine did we have altogether? What we had was 1, 2, 3. That's right, 4 chlorine. The product was, what was our final product when we did the reaction? Finally, what we ended up with was CCl4 plus how many HCl, hydrogen chloride, did we also produce? Have you written it out? Let's have a look and see. The answer should be CH4 plus 4Cl2 produces CCl4 plus 4HCl. I hope you got the same answer as me. So remember the basic stuff. Our carbon compounds are divided into 2 main groups, organic and inorganic. Organic means coming from living things. Our simplest organic compound is called a hydrocarbon, which can either be saturated, single bonds, or unsaturated, double bonds. The saturated hydrocarbons are called alkanes. They have the general formula CnH2n plus 2. When we name them, we use the given names, which are for 1 carbon meth, 2 carbons eth, and so on, prop, but, pent, and so on. You really must remember the name associated with the number of carbons. If you don't, you won't be able to write the right formula, and hence any equation you do is going to be incorrect. Remember their physical properties. They increase as they go down the homologous family, and the main thing is as the carbon atoms increase, mass increases, force of attraction increases, more energy is needed to overcome these forces of attraction. There are only 2 main reactions that alkanes do: combustion to produce carbon dioxide and water, and if there's insufficient oxygen, they can also produce carbon monoxide or just pure carbon. And finally, remember the substitution reaction that we've just gone through. So try to remember your alkane family and all the main points of your alkane family. They are the saturated hydrocarbons. That's all the time we have for this lesson. Thank you very much for watching ITTV.